we've talked about repeated addition is just multiplication. 2 plus 2 plus 2 plus 2 is there's 4 2's there. That's the same thing as 4 times 2. That's just 8. 7 times 5 is the same thing as 5 plus 5 plus 5. 6, 7 times. There's 7 5's there. You can also think of this as 7 5 times. I would probably think of this as 5 times 7, but that's the same thing as 7 times 5. Either way you do it, 5 7s, you're going to get 35 when you calculate it. That's repeated addition. Repeated multiplication is exponentiation. 2 times 2 times 2 times 2 is 2 to the 4th power. And that, if you multiply those all out, you get 16. This form here is called the factored form. 5 squared is the same thing as 5 times 5. But of course, 5 times 5 multiplication is just repeated addition. So we're going to have 5 plus 5 plus 5 plus 5 plus 5 is going to be 5 times. And that gives you 25. Now, we're not going to actually study repeated exponentiation, but I think it's just interesting to see because it's not something that you usually see. It actually has a few names because it's not quite an established, fully established, what exactly people use. But you could have tetration or super exponentiation. And there's a few notations of actually writing it. You could, of course, just write 2 to the power of itself 4 times. Use, instead of being 2 to the 4th power, you move the 4 before the 2. You can also use these double arrows. Either way you do it, they're all going to be equal to a very large number. Whereas 2 to the 4th power was 16. With the tetration here, we're going to get 65,536. So for 3, we're going to get 3 to the power of 3 to the power of 3. And you're going to start in the innermost part. 3 to the power of 3 is 27. 3 times 3 times 3 is 3 times 3 is 9. 9 times 3 is 27. And 3 to the 27 is going to be 3 times 3 times 3 times 3. 27 times. I'm not going to write that out. It's going to be too many, but I will use a calculator here to calculate it. And that gives me 3 to the power of 27. Quite a large number. I'm going to get 7625, 597, 484, 987. So we're going to have 1,000, million, billion, trillion. Extremely large for such small numbers that we're working with. That's the power of exponents, though. When you have a very large exponent, you're talking about a very large number. Okay, we talked about addition and subtraction being inverses, multiplication, division being inverses, exponents and roots are the inverses. So 2 to the 4th power equals 16. This is equivalent to the statement of 2 equaling the 4th root of 16. 7 to the power of 2 equals 49 is equivalent to 7 equals the square root of 49. Square roots are used so commonly that we actually just write it as without the power of 2 there. But the power of 4 in this case comes from the same power of 4 there. The power of 2 here comes from the same power of 2 here. Each exponent, 4 or 2 or whatever exponent, like 5 to the 3rd power, each exponent will have its own root. We'll always have the power and then the square root symbol. This is called the radical symbol. But that's how it's read. We're going to be working with roots much later on, not right now. They require other mathematics to explore really, but I just wanted to show you that exponents do have inverses, and they are roots. We can talk about perfect roots right now, but we need to have decimals otherwise, and because they're a lot harder to work with. Okay, we're gonna write these in factored form, and the root equivalent expression 5 cubed. This is the same thing as 5 times 5 times 5, which equals 125. If I write this as a square root or as a radical or a root, that's going to be 5 equals the cube root, because we have a 3 here. That's called a cube, or just the third root of 125. So this 5 cubed equals 125 is the same thing as that statement there. 3 to the 5th power is 3 times 3 times 3 times 3 times 3. This is the same thing as, let me do it on a calculator. I think it's, I'm actually not quite sure. 243. So that's the same thing as saying 3 equals the 5th root of 243. Once again, we're always using the same power on the root as the power on the number. 9 squared is 9 times 9, that's 81. And 9 equals the square root of 81. Once again, if you have a square root here with a power of 2, I showed before, you don't need to write the 2 here, but that's implied. Square roots are used so commonly that we just don't write the 2 there. Finally, we have 6 cubed is going to be 6 times 6 times 6. This is the factored form. And multiplying those together should give us 216, I believe. Let me double check. Yep, 216. So the equivalent root expression is going to be 6 equals the third root of 216. So base 10, I'm talking about exponents again. Base 10 actually refers to the power on 10, the exponent. So the ones place is 10 to the 0. That's defined as 1. The tens place is 10 to the 1. That's defined. That's going to be 10. Anything to the 1 power is just itself. 10 squared, 10 times 10 is 100. So that's going to be the hundreds place. 10 cubed is 10 times 10 times 10. That's 1,000. That's the thousands place. And 10 to the 4th power is 10,000. Then the 5th is 100,000s, and so on. So here we have 75,930. That's going to be 7 10,000s, 5 thousands, 9 hundreds, 3 tens, and 0 ones. That's the same thing as saying 7 times 10 to the 4, 5 times 10 to the 3, 9 times 10 to the 2, that's the hundreds place, 3 times 10 is the tens place, and then 0 times 10 to the 0 is the ones place. I can show you that this number, if we multiply all these things out, or do the operations, we can get back to here. But I haven't shown you how to do this operations, because we have operations within operations. If you have the same operation, it's easy to do. You just go left to right. But when you have different operations, how do we handle that? And the way we handle it is order of operations. You probably have heard of PEMDAS before, but that stands for parentheses is always the first thing you're going to do. Exponents is the next. Multiplication and division. This is technically done at the same time because they're inverse operations. They're really kind of the same thing, but you always go left to right, and then addition and subtraction are done at the same time. Again, left to right. Okay, let's see that in practice. There are no parentheses, there are no exponents. There is multiplication, so that's going to be done first. 5 times 2 is 10, and 8 plus 10 is 18. Once there's a single operation left, just do that operation. Here we do have parentheses, so this can be done first. 4 plus 2 is 6. And 24 divided by 6 is 4. Okay, here we have parentheses. That's done first. So we're going to get 8 minus 2 is 6. Okay, next we have no exponents. There is multiplication and division. So we're going to go left to right. So we're going to do the division first. 6 divided by 3 is 2. And then 2 times 4 is 8. And now, of course, we have 20 minus 8 is 12. Okay, now the fraction bar is acts like a grouping symbol, like a parentheses. If I put parentheses around the top and parentheses around the bottom, that's what the fraction bar implies. Make sure you always simplify the top and the bottom of the fractions before doing the division that results. So here we're going to have 10 times 3 squared plus 10 minus 4 is 6. 2 is just a number, so I'm just going to leave it as 2. There's no need to write the parentheses around that. Okay, I have exponents here, so that's going to be next. That's going to be 3 squared is 3 times 3 is 9. Okay, and then I have multiplication and division, so I want to do that next. 10 times 9 is 90. And 6 divided by 2 is 3. And of course, 90 and 3 is 93. Okay. Order of operations, right? There's going to be parentheses around the 8 plus 2 and the 7 minus 2. So I'm going to do those first and then take care of this and then do the exponent. That's what the parentheses are always done first. 8 plus 2 is 10. I can actually do the division at the same time because I have to do each one individually before I can do the division. So I'm going to do the bottom at the same time. 7 minus 2 is 5. So I have to take care of this division. 10 divided by 5 is 2. And 2 squared is 2 times 2, so 4. All right, let's keep going. Parentheses here. Let's go ahead and do both of those at the same time since I have to take care of both of them before I can do the division. 8 minus 2 is 6. 2 plus 1 is 3. Okay, exponents are next. 6 times 6 times 6 is 216. And notice here that I have pluses between all these numbers. Because of that, I have to simplify each one of these things. Addition is the last step in order of operations, right? It's done at the very end, which means I have to do the multiplication and division before I can do any kind of addition. In other words, I can do both of these at the same time since they're not going to affect each other until the very end. I have to do them both before I can do anything between them because the addition is always done last. So I can save some time by doing it in the same step. 2 times 216 is going to be 432. And 6 over 3 is 2. And now you can see I have addition all the way through. 4 plus 432 is 436, plus 2 is 438. So you can always do, as long as you understand which operations are done first, you can actually save some time and do things at the same time. Like for instance here, I know I have to do this first, but because of this subtraction here, that means I know that I could simplify whatever is here, but this of course is just a number. I can't do anything between these two until everything's simplified because subtraction will be done last. Unfortunately, on this side, I have division and multiplication, and both of those are done at the same time, so I can't just do the 5 times 3. I have to actually do this one first before I can, because then I would do the division, and then I would do the multiplication. So in this case, I can't actually simplify my steps down like I did in the previous one. 47 minus 2 is 45. Okay, there are no exponents, so division and multiplication. I'm going to do this one first, and then I'm going to do this one. That's going to give me 45 divided by 5 is 9. Now I can do 9 times 3 is 27. Now I can do finally I can do the subtraction. 51 minus 27. It's going to be 24. Okay. And here we have nested parentheses. I have to do this one, I have to do this one, and then I can do the addition. So I really need to follow order of operations in this case. Looking at the innermost parenthesis, you're always going to start at the innermost one first. 8 minus 2 squared. 2 squared is going to happen first because exponents happen before addition and subtraction. So I'm going to get 3 times 8 minus 4. 2 squared is 4. 8 minus 4 needs to be done next. That's going to give you 4. And then this is just multiplication here, so I'm going to write it as 3 times 4. Okay, now I have to take care of the 3 times 4, which is 12. And now I can take care of these brackets, these grouping symbols here. 12 minus 6 is 6. Finally, 15 plus 6 is 21. That's the answer for that case. Okay, a better way of describing order operations is with the acronym GEMA instead of PEMDAS. This stands for grouping, exponents, multiplication, and addition. There are lots of grouping symbols. We've actually seen a couple of them. We have parentheses. Square roots are actually going to be grouping symbols. Fraction bars, as we've seen. There's these things called absolute values that are going to be grouping symbols. Functions, which we're not going to talk about, but they are grouping symbols. There's many grouping symbols in mathematics. And so parentheses is just a single type of grouping symbol. And then as we can follow here, exponents is the same as PEMDAS. Multiplication and division, these two I showed you before. You can rewrite division as multiplication and vice versa. They're actually nearly the same thing. And so really they're done at the same time. You shouldn't think of multiplication and division as all that different. The same thing is true for addition and subtraction. That's why they're grouped together, multiplication and addition. So GEMA is kind of a better way of order of operations. And the whole point of it, the point of what we're trying to show, is that a higher order, the first things you do first, encodes more steps. And that can be seen here with exponents. 4 cubed is the same thing as 4 times 4 times 4, which of course, multiplication is just repeated addition. 4 times 4 is 4 plus itself 4 times. But that's being multiplied by 4, so you're going to have a lot of addition. 4 cubed is an extreme amount of addition, whereas 4 times 4 is a little bit of addition. It's more than just 4 plus 4, but 4 to the power of 3 is a lot of addition. So that has to be done first because it actually encodes a lot more steps that are be done at one time. So exponents must be handled before multiplication, and then multiplication is repeat addition. It's not just a single addition, so it needs to be done before addition. That's the reason why the order is as it is. Okay, and I was trying to show this before, but how you write your solutions is going to be important. You want to make sure you are trying to be very clear, and you don't have to name your steps, but you do want to be clear at what you're doing so that you can either look back or someone else can look at your solutions and understand what you're writing. You do not want to have errors, but as long as you're clearly writing it out, you should be able to catch your own errors. So let me show you that back to this problem that we had originally started with before talking about order of operations. This was the number 75,930. And I showed this using the actual meaning of our base 10 system as bases or powers of 10. And let's just prove that this does indeed equal 75,930. So first off, by order of operations, we're going to do the exponents first. 10 to the fourth power is 10 times 10 times 10 times 10, which is going to be 10,000. I can also, because there's addition here, I can do all of these portions. I can do all of these things at the same time because I have to do them. I have to simplify them down before I can do the addition. Exponents and multiplication are always done before addition, so we need to simplify them down first. 10 cubed is 10 times 10 times 10, which is 1,000. 10 squared is 10 times 10, which is 100. 10 to the 1 power, this is just 10. And 10 to the 0 power is 1. But we're multiplying that by 0. 0 times anything is 0, so this term goes away. Okay, now we have the multiplications. I can do all the multiplications at the same time. 7 times 10,000 is 70,000. 5 times 1,000 is 5,000. 9 times 100 is 900. And 3 times 10 is 30. And now if I line these up, doing the vertical addition that I've shown before, I'm going to line each place value up. You can see here that there's only one digit besides 0 in each of the places. So these add going straight down very nicely. 3, 9, 5, 7. 75,930. It is indeed the same number. So that's the idea here of what a number system actually means. It's just powers of 10 that are multiplying by certain digits to give you the place value. This is the place value of 10,000, and there's 7 10,000s in that place value. That's the idea. You can just do it for each of the place values, as you've seen here. And you can always double check my work to make sure I've done it correctly, because I have it clearly written what I have done. And so you could go back and check and double check to make sure I didn't make an error, but I didn't here. This is all correct. This was addition here. Okay, taking it step by step, right? Let's just do this and try and show a really good solution process to check your errors. Order of operations says PEMDAS, right, or GEMA. I'm going to use GEMA. Grouping symbols first. That's going to be the parentheses. So we're going to get 2 plus 4 times 8 minus 2 plus 3 is 5. And the next step is going to be, there are no more grouping symbols. Exponents is next. 5 times 5 is 25. Okay, multiplication and division. That's going to be 4 times 8 here, which is 32. Okay, now we're on to addition and subtraction. Addition is done first. It's going to be 34. And 34 minus 25 is the final one that we need to do. And that's just going to be 9. So you can see here with this good solution process that I've done only one step. And so it's very easy to check to make sure I've done it correctly. The first thing I did was get 5. Yeah, that's correct. Next thing was get 25. That's correct. The next thing was get 32. That's correct. The next thing was add to get 34. That looks correct. And finally, 34 minus 25 is 9. I can check my work very easily when you have good written out solution. Okay, Same process here. We have parentheses on top and bottom, so those need to be done individually. We're going to do multiplication and division first. There's no exponents here. So we're going to do multiplication first. So it's going to be 3 times 7, which is 21. And now I can do 5 times 2, which is 10. Those could be done at the same time because you have to simplify the top and the bottom before I can do the division. But just for the good flow, let's just show it individually. 9 plus 21 needs to be done before I can do the division. And 30 divided by 10 is 3. You can go back and check my work. It's all written there clearly. And you can see that I haven't made any errors.